In this exercise, we're going to look at a distillation column and control it with a PID controller. It's amazing how much energy distillation columns use within the United States. About 10% of the total U.S. energy usage goes towards separation processes, and about 6 to 10%, depending on which source you use, of that energy goes toward distillation columns in particular. So we'll look at particular. We're going to be separating cyclohexane from n-heptane. We're going to assume an initial reflux ratio of 3.0 and an allowable range from 1 to 10. This reflux ratio produces cyclohexane purity with 9.35 mole fraction, but the target composition is 0.97 with an allowable range of 0.96 to 0.98. The objective is to design a PID controller to meet this target value and stay within the specified product range. So to go ahead, our manipulated variable is going to be the reflux ratio, controlled variable is going to be the distillate composition, and then our measured disturbances are going to be the feed flow rate and feed composition. So we can see here feed and flow rate, the feed flow rate and feed composition are going to come in to stage 16. We'll then have relations that tell how each of these stages from 1 to 30 relate to one another and the compositions of each. And then the reflux ratio coming in will also affect all of these and the balance within the distillation column as a whole. As we return more, as we reflux more, we should get a finer product though. And so as we increase the reflux ratio, our molar fraction will increase as well. We have the initial states for all of those 30 stages, as well as the steady state initial condition. We'll go ahead and we'll simulate through 50 minutes and look at how things respond. We're going to store results for plotting, and then we'll step our reflux ratio to 5, down to 3.5, and up to 7. We then simulate this with the ODE45 that will go to our distill function, which takes 3 inputs: the reflux ratio, the feed rate, flow rate, and the feed composition. That will then go toward this X states, which is the mole fraction at each state from 1 to 31. So then we have our distillate flow rate. We have our flow rate of the liquid in the rectification section, the flow rate within the column, relative volatility, total molar hold up, and then what we'll do is we'll loop through each of these stages, and we'll relate the volatility equal to the volatility minus 1, subject to the molar fraction at that point. Basically what we're doing here is we're having some molar fraction in the liquid, relate the volatility total to the molar fraction within the vapor here. With this vapor coefficients, we're able to compute how much mass is transferred back and forth. We'll go ahead and do that here with this x dot, and then x dot for the upper stages, and then we'll return x dot, the change in concentration over time. So we'll go up here, we'll obtain our PID tuning constants. So we'll go ahead, we'll run our first section. And the second one. What we'll do is, I'm worried about a little bit about overfitting our solution. And so once we start to flatten out, I'm going to go ahead and say that's good. You can see right here, FOPDT overestimates how much this step up to 7 will do. That's because this is a nonlinear system, and so as such, the response is not linear, it's not proportional. You can see it kind of tapers out at 1. So maybe a better thing to do would be to get a better accurate fit for what we are doing. So let's say we go up to 5, down to 3.5, and then up to 4.0 instead. We'll go ahead, we'll simulate that, and then we'll run this section as well. So that's decently accurate. Let's focus just on the PID control here for a moment. So our PID control is where we're right here. We'll use our tuning constants, and we'll go ahead and start there. We've done tuning constants enough. I figure I don't need to go into it. We have a process variable starting initially at 0.935, and then we'll set the set point to 0.97 after 100. We have our initial states, and then our OP high and our OP low are our outputs. Let's go ahead and see how well this controller performs. We can see we reach this 0.94 set point, and at 10, we go up and we push toward this 0.97. You'll notice we really want to stay within the 0.96 and underneath the 0.98, and we're able to do that fairly well. There's a decent rise time, and we don't have any overshoot, any instability or oscillations. So what we're going to do is we're going to set the set point like we did from 0.935 to 0.97, and we're going to define what constitutes best performance. So as well as generating a plot, explain what criteria we use to define best, I would say error once we reach the set point, being able to stay at the set point, rise time to go to the set point. All of those would be important. In addition, we have a valve, and so we don't want to have chattering with our valve. So we want this to be smooth, not too many oscillations. Now what we're going to do is after 50 minutes, we're going to change the mole fraction from 0.5 to 0.42, and we'll simulate the controller, and we'll tune it to stay within desired range. So we'll come up here, we'll say NS is equal to, what was it equal to before? Length of T, and T was 500. So we'll say it's equal to 1,000 now. Then, as we're doing this, we want to say that our X, I'm looking for where that feed fraction is. Right here. Let's take this, and we're going to put it down there as well. So XD is the mole fraction of the distillate. RR is the reflux ratio. FF is the flux rate, and XF is the distillate flux fraction. And so we'll go ahead, we'll say that XF from 500 to the end is equal to 0.42. And we'll see how well our controller performs with this deviation now. So we'll go ahead, we'll run this section. Index must not exceed 500. So we also have our T that must be reinitialized. We'll go ahead and do that. We'll make NS 1001. So let's go ahead. We'll try running it again. There may be some other error that happens. Index. So what was the index now? Must not exceed 100. So T is 1 by 100. So T, right here. So T, we're going to go from 0 to NS minus 1 divided by 100. So we're going to go to 0 to 100 with 1,001 points. So now everything should be the same. Here's our set point. You see, even though our process variable starts going up, our set point goes down, or I should say our measured data goes down. And we go all the way down to 0.8085, even when our process variable is going all the way to 10. And so that's alarming. That's not what we want, and our process variable is responding. So what we're going to try to do, let's try to tune up our integral control a little bit. So right now our integral is at 0.4. I'm going to go ahead and comment that out. Let's change it to 0.2, or to 2, I should say, rather, from 4 to 2. So we're staying better around there. We have this offset that continues to occur. So our Kc is equal to 3.1. Let's go ahead and change that to, let's say, 3.5. And this 0.2, let's say 1.5. I accidentally started the whole thing running. That should be fine. Let's run this section again. So it's doing better. It's staying there longer, and it's kicking up to the ideal concentration. We'll note that we're still deviating. We're still going off too far, and that's largely due to the fact that at 0.42, I think it becomes impossible for us to stay there. So our 0.42 change happens right there. And as we start sliding away, we kick up to the process variable at 10, our limit, and we're still not able to maintain it there. So my thought is, let's go ahead, let's just try a little bit more tuning, and if not, it may just not be possible. So we'll change this. Let's change this to 45. Let's change this to 1.0. Make sure that ran. Again, we do kick up. We see that staying up there, but eventually it stays up too high, which is too bad. Let's make sure that it's because of that change in our feed concentration. If I were to comment this out, the feed concentration would stay at 0.5. If that were to happen, it does stay there. In fact, we overshoot. But we overshoot to 0.98. That's not a big deal. So it is due to that feed change. Let's go ahead and read our instructions for the second portion again, this disturbance reduction. So introduce a disturbance in the feed after 50 minutes by changing the mole fraction from 0.5 to 0.42. Tune the controller to stay within the product range given this disturbance. If the controller isn't able to keep within the desirable range, discuss if it is possible to improve the control. So what have we found? As we do this change, it eventually goes out of range. And why does it do that? Or we become saturated and we can't, what happens when let's just run this section and discuss it. So if we scroll down, at 0.5, we start getting less of the product that we desire in. It takes a while for that balance to happen where there's less coming in. It's still going to be initially some of our distillate in the mole fraction we desire, but as less of it continues to come in, we start increasing our reflux ratio all the way to 10, but there's still just not as much that we can get out, and so that's why we start going down. There's a certain mole balance that has to be maintained, and so even if we're refluxing at this rate, it's not possible for us to draw out as much as we would like. So that's where we say it's probably not possible. Then we're going to do distillation simulation code. That's what we have already. So there we go. If we were to, let's say our feed, let's say that happens. How can I say? One way to check, let's try one more way to check whether it would be possible, and that's just instead of it being at 0.2, let's say we're something like 0.45, a little bit more reasonable. Would we be able to get there? So we'll go ahead. I'll let this run just a bit. Fitting. Actually, we've already done our fit. We do that to get the PID constants. So let's go ahead and look at performance. I'm going to run this section again. We still see some oscillation and then it plummeting down. If I were to, let's say, tune this to, and this is we may be pushing the limits of stability, but to 0.5 integral control. We'll run this section, and we'll see even then we have this oscillation, but we reach saturation and it still goes down even when it is saturated. Integral of error is only increasing. It is very small though, this integral of error. I will know. Actually, let's look at the actual values here. So if we were to change instead our reflux ratio possibly to 20, let's see if we would be able to get there. Even then, we still go up to 20, and the slope is better. We're still not all the way there. If we were to be able to go up to 100, could we get there? Obviously, this is a nonlinear process, so we can't expect... did that again. Go ahead. We'll stop. We'll run this section. If we could do 100 in the reflux ratio, run section, we still would not be able to. So that we don't quite get all the way. So let's go ahead, let's try increasing our KC a little bit. See if even at 100 we'd be able to control it right. Let's set our KC to, let's say 60. We'll run the section. And it's better, but we're still not able to. So as a property of the molar balance, let's go ahead and I'll just really quickly draw it out. In has to equal out. And so when we come in, let's take out really quick. Let's come up here, let's look at our constants. The distillate reflux ratio. So feed rate is at 1, and it's at 0.5. And how much is coming out in the distillate? Let's look at our function. Distillate flow rate is 0.5 times feed, so half the feed is going into the flow rate. So let's just do this okay, that makes a lot of sense, and we can justify our results. We'll just use this white space here. So in is equal to out. And out has two forms. It has distillate, and it has the bottoms product. So if we have 0.5 coming in, and we want our distillate to be 0.97% pure, well, that's possible because 0.97% would be, and we have in the distillate 0.5 total. That would mean that for the distillate coming out, the total molar amount is 97% of 0.5. And so that's going to be 0.485. So then if we think about, so that's the amount we want coming out at the end of the reflux ratio. So we have the reflux coming in, we have the part that refluxes out, and the part that we want to be our product, we want 0.485. Now if we have 0.42 coming in, there's no way to get 0.485 coming out. It still is half of whatever's coming in is going to need to be coming out. And so there you have it. whatever's coming in. So if we have 0.42 coming in that ratio, that means that we have, of the whole 1 mole coming in, 0.42 of it is the compound that we care about, and there's no way to change 0.42 into 0.485. So even if we had 100% conversion in this separation reaction, the most we could get out is 0.42, or about 84%. And so there may be a little bit of a change. As we reflux more, we can hold on to, we can separate more and more and hopefully get every last little bit separated out and into the distillate product. But eventually we'll reach a new steady state with this 0.42, and at that point there will be no way to extract up to 0.485 moles. So hopefully that makes sense. This is a good exercise in talking about not only control and looking at our controller, but an exercise in looking at whether it's even possible to do what we're hoping to do.